This is chapter 6, question number 15 from the 7th edition and question number 13 from 6th edition. It says the person inherited some items which appreciates. These are the items which appreciates in the value from every year. For the predictions, the future predictions are present for like 5 years. Sometimes it appreciates by 1 unit, and sometimes the difference is just 2 units, and sometimes it's just one, sometimes it's three, like an example of the desk. And this is the yearly value of particular items for 5 years. And the person has a propensity to spend, and he needs at least 30,000 funds each year for tuition fees. And the financial advisor, has to develop a plan to dispose these assets that will maximize the amount of money received at the end. So, to formulate the IOP for this problem, we need to find what are the variables. What can be the variables here? If we look at this, this item and the values each year, the objective is to sell all these items and to have maximum refund value. This refund is nothing but total amount of money that is collected from selling this item. Well, on an ordinary case, every item appreciates, so one can sell all the items at the year 5, which would give the sum of all this as the maximum return value. But there is a constraint that wants to make sure that every year they sell at least something, that they get at least 30,000 for expenditures every year. So if they sell the car in the first year, they don't need to sell anything here in the first year. In the second year, this car would be already sold, so it cannot be sold further. So in the second year, if they sell let's say the desk, then they have to sell some more things like the humidor, let's say. Then it would be, let's say it is 35, and this would be 34. If they sell this desk in the second year, they cannot sell the desk again, and they cannot sell the humidor again, and in the next year they have to sell something else in order to make another 30,000 grants. So they can sell the golf clubs. This is just an example. This is not the solution, I'm telling you. This is just an example. Now if they sell the golf club, they cannot sell it in the final year. And in fourth year, they have to sell something to make $30,000, and they have got two options left here, 139.19. So they can sell the necklace, which is like this and cannot be sold here. It would be 139, and only last one items remaining, but have to collect at least 30,000 here. So see, this is how we should do it, but here it's only 20, but we need 30. So we have to decide in such a way that every year they collect 30,000 rupees, and 30,000 rupees to make this constant valid, and sum of this return value should be maximized. In order to do that, we have to find the variables. What can be good examples of variables here? The example of a variable would be like whether this item has to be sold in year 1 or year 2 or year 3 or year 4 or year 5. Similarly, whether this item has to be sold in year 1 or year 2 or year 3 or year 4 likewise. So let's consider this is item 1, 2, 3, 4, 5 and 6. Our decision variable, as you can recollect from the previous examples that we have worked out, in any scenario, if we have a clause if this else this, or an example where it can be done in just two ways, in that case we always go for binary variable. So if we consider this as a binary variable, that is x 1 1, is nothing but x ij, where I represents the item and j represents the year. So if x11 is binary, that means item 1 sold in year 1. If that is equals to 1, then car has to be sold in year 1. If that is 0, car is not sold in the year 1. Similarly, other variables x21, x23, x24, x25 and x26 could represent, my bad, x11, x21, x31, x41, x51 and x61 will represent the decisions to sell the item I in the year 1. It is x I 1, items to be sold in the year 1. Summation of it will give the value of the item sold in year 1. Let's go back and make the decision variables. Let's consider x ij as the item I sold in the year j, where I equals to 1 for car, 2 for piano, likewise, and 6 for humidor, and j represents year 1 to 5. So how many variables? There will be 6 cross 5, 30 binary variables. and this is the selling price. So let's consider this as the selling matrix Sij, and the matrix provided with the yearly cost be Sij. That is selling price of item I in year J. Now let's and just put where I is equal to this and this. Now what is our objective? Our objective is to maximize the amount of money received. That is, maximize summation of Sij multiplied by Xij. This is our objective. And what are our constraints? Our constraints is that this xi1, summation of xi1, summation of xi2, summation of xi3, xi4, that is the amount collected in the year 4 and year 5. These values should be at least 30. So let's say insert summation of xi1 greater than equals to 30. Same you can write as xi2 greater than equals to 30 likewise. Or you can say like, instead of writing it 5 times, you can write as summation of xij is equal to 30 for all j equals to 1 to 5. The same thing. Just like this is the column sum, right? This is for particular year. J is for particular year. J is for the particular year. This is a column sum. Column sum product with this distant variable should be greater than 30. Now what should be the row sum? This item can be sold only once. Similarly, this item can be sold only once. So if you sell it here, you cannot sell it here, you cannot sell it here, you cannot sell it here. And these all are binary. So this is 1. So the row sum should be 1 for each item, because we have only one item of each, one quantity of each item. So the row sum should be 1. So we should have have another constraint is equals to 1. This would be similar to that of instead of writing x 1j is equals to 1, x 2j equals to 1. Likewise, we can just write it as xij is equal to 1 for all i from 1 to 6. Now this is the row sum. In this we are forgetting something. It has to be the sale of product in each year, right? And we are forgetting something here. There should be two summations. Why? One is for each row of the year and one is for each item of the year. Here this is Sij will represent this cost, this selling price matrix multiplied by the decision matrix, like the decision to sell or not. So for particular year J, summation of the selling price into the decision price will give the amount of funds collected by selling items. Okay, so these are the two constraints that we have. This is for the row constraints, that is item, or let me write it here, row constraint that signifies quantity of each item This is the columns constraint that signifies the amount collected from sale of items in each year. Now suppose there is a big twist in the question, like there is two quantities of the car. In that case, what should be the constraint? Instead of x 1j is equals to 1, is equals to 1, it will become 1j is equals to 2. If x 1j is equal to 2, that means number of time x1, that is item car, is sold is 2. That means there are two quantities of car that can be sold. If it is 3, then there are 3 quantities of car that can be sold. This is just for your knowledge. This is not related to the question. Okay. Now let's transfer this LP into our spreadsheet. I just prepared the initial price or the selling price for the items in the years, so that I won't waste time on this. So the decision matrix will look something like this, with these values as binary and this will be the decision variables. Let's make me as gray, and let's say minimum funds each year is, let's say, 30, right? So this equals to sum product of, if you see, sum product of the selling price matrix in the decision variable for each j. For this is not for all j, for each j from 1 to 5. So sum product of this multiplied by this. This is the funds collected. Okay. Now I will extend this formula for each year. Let's say it's all good. Yeah. And this is our column constant. This should be greater than equals to the minimum funds needed each year. And we have one more constraint, that is equals to sum of all these decision variables, and this should be equals to 1, right? So this is the row constraint, should be equals to 1. So what is our objective? Our objective is to collect maximum funds. This is where you collect the funds, right? Is equals to total fund collected total fund collected is equals to sum of all these, and this is make it green to make sure it is an objective function. Now let's go back and fill the solver. Okay. Button solver. Maximize that cell by changing these cells subject to the constraint, and all these cells are binary, and these values should be equals to 1, and these values should be greater than equals to this value. See, either you can hard code here 30, or you can refer it to a cell. It's always good to refer it to a cell, because suppose tomorrow the minimum funds needed each year becomes 35, you can just change it in the cell and run the solver. But if you put in the solver as half coded 30, you have to go and find it in the solver and do it. So the best practice would be to keep it in the spreadsheet and run the solver. Okay, and what else constraints? We have binary constraint. This is the row constraint, and sorry, this is the row constraint. This is the column constraint. All right, and let's make it simplex. So 274 is the maximum fund collected. Now that you have got the solution here, 274, the point is, in this we have, there's a bit trick involved here, just be careful. This is fine, like it satisfies all your constraints and gives you an very optimal return. That's fine, but there is a little problem in this. This optimum value that you got may not be completely optimal because we have run simplex LP. In these cases where there are a lot of variables used, there are so many sub problems and so many iterations involved. When you use simplex LP, it doesn't take into consideration the precisions. It just takes a very small precision, and within 1% optimality, it ignores other solutions. So if you look at GRG nonlinear or evolutionary, you can give what is the maximum optimal difference, and you can increase the number of sub problems, thereby having a better chance of having a better optimal solution. So to do that, let's do it as GRG nonlinear. We had 274 collected, and if we solve it through GRG nonlinear, you can see here number of sub problems and the trial solutions. It is working out to a very high precision. You can see the values over here. It is working out to with very high precision of 5 to 6 digits of decimal to get this optimal solution. We'll just wait. Just carefully watch. This 274 will change. An optimal solution can be within 1% or a few percent of optimality. When you're doing simplex LP, anything within 1% or close to 2% of it's not hard on 1% or 2%, somewhere close to the optimality, the trial or the loop of finding more solutions stops. But when you choose GRG nonlinear and choose the precisions, it work out more number of trials and more sub problems to find much better solutions. That's the reason why the professor, they always recommend to use the analytics solver platform instead of using the Excel provided solver add-in. You can see here, like they have tried 290 sub problems, with each sub problem having so many 12, 10 trial solutions. See, after so many sub problem and trial solution, it found 275 as the final most optimal solution.